Blackbody radiation and Wien's law. You'll be aware that a red object appears red because it reflects red light and absorbs all other colours of the spectrum. Equally, a black object absorbs all colours. It will also, when heated, emit all colours to form a continuous spectrum. This is what is known as blackbody radiation. This shape represents a horseshoe being heated by a blacksmith. As it gets hotter, it will emit more radiation, but also the proportion emitted at different wavelengths will vary. And we'll see this in the colour change. Initially it will go dull red, then bright red through to orange, eventually becoming yellow, and if heated sufficiently it will become white hot and then even take on a bluey tinge. We see the same colours with stars at different temperatures. Cooler stars can appear red, the sun is clearly yellow, and hotter stars can take on a bluey tinge. Let's look at this in a little bit more detail. Here we have a graph of the intensity of the radiation against wavelength for a black body, which could be a star. I've put on the visible part of the spectrum just for reference. This is a star at around 3000 Kelvin. You'll see it gives off a small amount of radiation at the high energy short wavelength radiation. It's peaking beyond the red part of the spectrum and then falls off towards even longer wavelengths. If we look at a different star at, say, 6000 Kelvin, we'll see that overall this is a higher curve. The hotter star is giving off more radiation, but it's also peaking further to the left, so it's giving off a greater proportion of its radiation at higher energy, shorter wavelengths. This star would be giving off a significant amount of light in the visible part of the spectrum, and our Sun is at round about 6000 Kelvin. At 12,000 Kelvin, this star has a higher line still, it's giving off more radiation, but now the bulk of the radiation is at shorter wavelengths than visible light. This star would have a bluey tinge to it. Now for a clearer comparison, I'll plot the lines of intensity against wavelength for black bodies at several different temperatures on the same axes. Starting off with a line for an object at 3000 Kelvin. The 4000 Kelvin object has a overall higher line, it gives out more radiation, but it also peaks at a shorter wavelength. The trend continues with 5000 Kelvin peaking at a shorter wavelength still, and finally the 6000 Kelvin line, which peaks here. Adding the visible part of the electromagnetic spectrum, just for clarity, you'll see this equates to roughly the temperature of our Sun, which appears yellow. The peaks of the lines, here, 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 and here, I'm going to refer to as lambda max, the wavelength lambda at which we get the maximum intensity of electromagnetic radiation given off by the object. If we join these peaks with this dotted line, we see there's a clear trend going to shorter wavelengths as the temperature of the black body increases. This relationship leads to Wien's law, which is that lambda max times the temperature in Kelvin is equal to a constant 0.0029 meters Kelvin. Don't forget, lambda max is the wavelength at which the object gives off its maximum intensity of radiation. So, if we observe a star and find that its peak wavelength is 0.75 micrometers, we can rearrange the equation above and put in the values for the constant 0.0029 and the lambda T max down here, and we get that the temperature of the star is 3900 Kelvin.